Hi, welcome back to the solutions manual. In this video, we will solve the problem F6-6 from RC Hibbeler Engineering Statics 15th edition. According to this problem, we have to determine the force in each member of the truss and state if the members are in tension or compression. Now to solve this problem, first of all, we have to draw all the support reactions. So at joint A, I have a pin support, so I have a vertical support reaction and the horizontal support reaction. At joint C, I have a roller support, so I have a vertical support reaction. Let's label them. So this right here is AX, this is AY, and this is CY. Now we can apply the equations of equilibrium to find the support reactions. So our first equation is summation of moments at point A equals to 0. I'm considering counterclockwise direction as positive. So AX and AY will not produce any moment about point A because they are passing through it, so they don't have any moment arm. The line of action of the 6 kN force is passing through the joint A, and since this force is passing through the joint A, so this force will not produce any moment about joint A as well. This CY force is trying to rotate the truss in counterclockwise direction about joint A, so the moment produced by this CY force will be taken as positive. And the moment arm is this 6 meters distance. 4.5 kN force is trying to rotate the truss in clockwise direction about the joint A. So the moment produced by this 4.5 kN force will be taken as negative. And the moment arm is this perpendicular distance. Let's call this X. And to find the value of X, we can consider this triangle, which has an angle of 30 degrees and a base of 6 meters. So tan 30 is equals to opposite, which is X over 6. So X comes out to be 3.464 meters, which is our moment arm for the 4.5 kN force, equals to 0. So from here, CY comes out to be 2.6 kilonewtons. Similarly, for the AY force, we can do summation of forces in Y direction equals to 0. I'm considering up direction as positive. So we have AY plus CY minus 6 equals to 0. So AY plus CY, which is 2.6 minus 6 equals to 0. So from here, AY comes out to be 3.4 kilonewtons. And for the AX force, we can do summation of forces in X direction equals to 0. I'm considering right hand side as positive. So we have negative AX plus 4.5 equals to 0. So AX comes out to be 4.5 kilonewtons. So these are our support reactions. And now we have to determine the force in each member of the truss, for which we are going to use the methods of joint, in which we will draw the free body diagram of each joint, and then we will resolve the forces into their components if required, and then we will apply the equations of equilibrium to get the force in each member of the truss, and to determine its nature as well, whether it is a tensile force or compressive force. So starting from the joint A, the free body diagram of a joint A would look something like this. So I have a force AY towards the joint. I have a force AX which is away from the joint. I have a force due to this member AE, and I am assuming it as a compressive force. Also, I have a force due to this member AB, and I am assuming it as a tensile force. Let's label them. So this right here is AY, this is AX, this is FAB, this is FAE. And now we can apply the equations of equilibrium. So our first equation would be summation of forces in Y direction equals to 0. I'm considering up direction as positive. So we have AY minus FAE equals to 0. So FAE is equals to AY, and AY came out to be 3.4 kilonewtons. And since we are getting a positive answer, so in fact, force in the AE member is compressive. For the force in the AB member, we can apply summation of forces in x direction equals to 0. I'm considering right hand side as positive. So we have FAB minus AX equals to 0. So FAB is equals to AX, which we have calculated as 4.5 kilonewtons. And since we are getting a positive answer, so it means FAB in fact is a tensile force, because our assumption is correct, and that's why we are getting a positive answer. Now we have to repeat the same procedure for the joint E as well. So let me just copy this image. So for the joint E, the free body diagram of the joint E would look something like this. I have a 6 kilonewton force acting in a downward direction. I have a 4.5 kilonewton force acting towards the point E. I have a force due to this member ED, and I am assuming it as a tensile force. I have a force due to this member EB, and I am also considering it as a tensile force. Similarly, I have a force due to this member AE, and the force AE is a compressive force, so acting towards the point E. Let's label them. So this right here is 6 kilonewton force. This is 4.5 kilonewton force. This is the force FED. This is the force FEB. And this is FEA. If I draw a horizontal line here, then this angle is also 30 degrees because it is alternate to this 30-degree angle. So they are same. So this angle right here is 30 degrees. If I draw a horizontal line here, to find this angle, let's call this angle theta, which is same as the angle right here. So if I draw a triangle to find this angle theta, the base of this triangle is 3 meters and the height is 3.464 meters. So tan theta is equals to opposite over adjacent. So theta is equals to tan inverse of 3.464 divided by 3. So theta comes out to be 49.1 degrees. Now we can resolve the FEB force and the FED force into their components. So I have a horizontal component and the vertical component, a horizontal component and the vertical component. So let's label them. This right here is FED cos 30. This is FED sin 30. The horizontal component of FEB is FEB cos theta, and the vertical component is FEB sin theta. So I hope the free body diagram for the joint E is clear to you all. Now we can apply the equations of equilibrium. So we have summation of forces in y direction equals to 0. I'm considering up direction as positive. So we have this negative 6 kilonewton force, and we have a force FEA. I should call it FAE because earlier we have used the term FAE. So I should keep it the same. So FAE. Plus FAE minus FED sin 30 minus FEB sin theta, and theta is 49.1 degrees equals to 0. So when I put the values and if I simplify it, so minus 6, the value of FAE force is 3.4 kilonewtons minus 0.5 FED minus 0.76 FEB equals to 0. Upon further simplification, we have 0.76 FEB plus 0.5 FED equals to negative 2.6. So this is our equation 1. And you can see that we have two unknowns in this equation, force FEB and FED. And we have only one equation. So we have to form the second equation. So our second equation would be from the summation of forces in x direction equals to 0. I'm considering the right hand side as positive. So we have FEB cos theta, and theta is 49.1 degrees. We have FED cos 30, and we have this 4.5 kilonewton force. Equals to 0. So when I simplify it, the above equation becomes 0.65 FEB plus 0.87 FED equals to negative 4.5. So this is your second equation. So now we have to consider the equation 1 and 2, and we have to solve them simultaneously. So if I consider the equation 1, and if I make the FEB the subject of my equation, I have negative 2.6 minus 0.5 FED divided by 0.76. So let's call this equation 3 and substitute it in equation 2 in place of FEB. So equation 2 becomes 0.65 FEB, and now in the place of FEB we have negative 2.6 minus 0.5 FED divided by 0.76 plus 0.87 FED equals to minus 4.5, and upon further simplification we have 0.65 into negative 3.42 negative 0.66 FED plus 0.87 FED equals to minus 4.5. So upon further simplification, FED comes out to be negative 5.2 kilonewtons. And you can see that the answer is negative. And earlier we had assumed FED to be a tensile force. So in fact, it is a compressive force. Now to calculate the value for the FEB force, I can put it back into the equation number 3. So FEB equals to minus 2.6 minus 0.5 into negative 5.2 divided by 0.76. So you can see that it's negative 2.6 and the product will give me positive 2.6. So FEB comes out to be 0. So it means the member EB is a zero force member. So it is neither in compression nor in tension. Now we have to repeat the same procedure to find the other forces in the other members. For the joint D, the free body diagram of the joint D would look something like this. I have a force because of this member ED, which came out as a compressive force. This is the FED force. I have a force due to this member DC, and I am assuming it as a tensile force, member in tension. And I have a force due to this member DB, and I am assuming it in compression. So let's label them. This right here is FDC, this is FDB, and this is FED. And since I have correctly drawn the direction for the FED force, which is compressive, so I no longer have to put the negative sign with the 5.2 kilonewton. I can just put the positive sign because I have correctly drawn its direction this time, which is the compressive in nature. It's just the 5.2 kilonewton. And if I draw a horizontal line here, then this angle is also 30 degrees because they are alternate angles, which is same as this angle. And since these two are the vertically opposite angles, this angle is also 30 degrees. So now we can resolve these forces into their components. So we have one vertical component and one horizontal component. Similarly, one horizontal component and one vertical component. So let's label them. So this right here is FED sine 30 degrees. This is FED cos 30 degrees. This is FDC cos 30 degrees. And this is FDC sine 30 degrees. So now we can apply the equations of equilibrium. So first equation would be summation of forces in x direction equals to 0. I'm considering the right hand side as positive. So we have FED cos 30 plus FDC cos 30 equals to 0. And the value of FED is 5.2 kilonewtons. So 5.2 into cos 30 plus FDC into cos 30 equals to 0. So from here, FDC comes out to be negative 5.2 kilonewtons. And as you can see here, the answer for FDC is negative. And I had assumed FDC as a tensile force. So in fact, the member BC is in compression. Now to calculate for the FDB force, we can apply summation of forces in y direction equals to 0. I'm considering up direction as positive. So we have FDB minus FED sine 30 minus FDC sine 30 equals to 0. So we have FDB minus 5.2 into sine 30 minus FDC, which is negative 5.2 into sine 30 equals to 0. So from here I have FDB minus 2.6 and plus 2.6 equals to 0. So FDB also comes out to be 0. So the member DB is a 0 force member. It is neither in compression nor in tension. So far we have calculated for the member AE, ED, EB, AB, and DC. Now we have to work for the member BC. To find the values for the member BC, we have to consider the free body diagram of the joint C. So if I just zoom out, so the free body diagram of the joint C would look something like this. I have a vertical support reaction because of the roller at C, so Cy. I have a force because of this member DC, which in fact is a compressive force. I have a force because of this member BC, and I'm assuming it as a tensile force. So let's label them. This right here is the force Cy. This is FDC. And since I have correctly drawn its direction, which is compressive in nature, so I no longer have to put the negative sign with the 5.2 kilonewton. It is just 5.2 kilonewtons. And this angle is 30 degrees. So this right here is the 30 degrees. And this is the force CB. So let's resolve this FDC force into its components. So I have one vertical component. So I have one vertical component and one horizontal component. Let's label them. So this right here is FDC cos 30 and this is FDC sin 30. Now we can apply the equations of equilibrium. So our first equation would be summation of forces in x direction equals to 0. I'm considering the right hand side as positive. So we have FDC cos 30 minus FCB equals to 0. And the value of FDC is 5.2 kilonewtons. So 5.2 into cos 30 minus FCB equals to 0. So from here, FCB comes out to be 4.5 kilonewtons. And since we are getting a positive answer, it means the FCB is in fact in tension. So let me summarize it, the whole solution. So AX is 4.5 kilonewtons, AY is 3.4 kilonewtons, CY is 2.6 kilonewtons, FAE is 3.4 kilonewtons and it is compressive. FAB is 4.5 kilonewtons and it is tensile. The member is in tension. FED is negative 5.2 kilonewtons. And since we had assumed it as a tensile earlier, but we are getting a negative answer, so the member ED is in compression. Similarly, the force in the member DC is also negative 5.2 kilonewtons, because earlier we had assumed it as a member in tension, but as we are getting the negative answer, so it means the member is in compression. The force in the member CB is 4.5 kilonewtons, and the member is in tension. And the force in the member EB is equal to the force in the member DB equals to 0, because these are the zero force members. So they are neither in tension nor in compression. So this is it for this problem. I hope you will find this video helpful. If you do, please make sure to subscribe to this channel and also turn on the bell icon for the daily updates. And if you have any questions or any doubts, then feel free to ask in the comment section and I will answer it as soon as possible. Thank you.